Welcome back. In the second part of the presentation of controller for solving the trajectory tracking problem in the joint space for robot, we will consider two types of further control design. The first one is based on the full nonlinear model of the system, but achieves global asymptotic tracking of the trajectory without requiring complete cancellation of its dynamic. The second type of controller is instead based on very little information about the model dynamics and achieves again perfect reproduction of the desired trajectory in case the trajectory is repetitive, so that we can allow repeated trials in order to improve the performance. So with this in mind, let's start with the first controller. Takes the following form like it is written in the slide. Indeed, it's similar to the feedback linearization controller, but there are some differences. First of all, the proportional and derivative terms with respect to the error are not premultiplied by the inertia matrix. And then you see that there are some variables that are computed on the desired quantities. In these particular cases, I added also a viscous term, a viscous friction term, in order to highlight if such terms should be evaluated on the actual velocity Q dot, or rather, like they should, on the desired velocity. Now, there are a couple of assumptions that we made. We assume that in this control law, we use a special factorization of the coherence and centrifugal term, namely the one that guarantees that the matrix m dot minus 2s is Q-symmetric. Since we are using this factorization in the design of the control law, of course, we have to make sure that this condition is satisfied. For the PD gains, we have the usual standard assumption, so positive definiteness and without loss of generality, symmetric gain matrices. Now, we would like to show that this is in fact another controller that achieves global asymptotic stability of the error position and velocity, so that we guarantee asymptotic trajectory tracking. The proof is much more involved than in the case of feedback linearization. Essentially, in feedback linearization, we use a nonlinear control in order to cancel all nonlinearities. So, on the linear side of the resulting problem, we stabilize the trajectory error by choosing simple gains, and the analysis is trivial because it's made on the localization of the poles of the transfer function of the equivalent single input, single output system. In this case, we require the full machinery that we have seen on stability, namely Lyapunov, and not only LaSalle, but in the present case we need to use the farthest theorem that we just highlighted in the introductory part of this control lectures, namely the Barbalat lemma, which will guarantee that we can use LaSalle even in the present case where the closed loop system is a time-varying one, and it's a time-varying one because there's a dependence on the desired trajectory, and we will see this in detail. So the proof is much more complicated. And in fact, this controller, it's quite obvious, it will be very clear in the proof, does not imply or produce a complete cancellation of the nonlinearities of the dynamic models. As a rule of thumb, this type of controller is obtained by replacing everywhere velocities or acceleration appear in a linear fashion in the model, so in the inertia term, and the outer term of the co-resistance centrifugal factorization. And in this particular case, the only velocity that is present in the dissipative term, then this should be set at their desired value. And we will see that this has some consequence, allows us to prove asymptotic stability in a global sense. So, as a consequence, since we are not cancelling nonlinearities, the closed loop system will still be nonlinear and coupled. So, the message to take home in this case is that we don't need to do this nonlinear cancellation by feedback in order to obtain global asymptotic tracking, and we don't need to have a linear and decoupled closed loop system behavior, although this has a lot of nice consequence. So why we are introducing this alternative trajectory controller? Essentially because this control law, as opposed to the feedback linearizing one, lends itself relatively easy to an adaptive version. So in case we don't know exactly the model parameter, or we don't know them at all, we would like to move to adaptation, and we will see this in the next lecture. One last comment, indeed this control law, apart from the PD part, which is simply added to whatever dynamic computation, so the first four terms cannot be computed by the standard Newton-Euler algorithm. Why is that? Because the co-resistance centrifugal term, in fact, is evaluated both with the current velocity Q dot and with the desired velocity Q dot desired. So the standard Newton algorithm takes only 3 arguments in input. We will choose the configuration Q, through which we evaluate the gravity term, the inertia matrix, and also the factorization matrix S. We enter as a second argument Q dot because we need it inside this S matrix, but then we have no space for entering also a Q dot desired, which is different from the argument inside the matrix S. And then, of course, we may use the acceleration desired Q double dot D. So, we have already mentioned that there's a possibility of extending the Newton-Euler algorithm with a fourth input, and this global trajectory controller can in fact be evaluated with the modified Newton-Euler algorithm, so still efficient. So let's look at the proof. The proof, as I said, is quite difficult to follow because we require a number of mathematical tools. Anyway, let's try to look at this together. So we have the robot dynamics, and we include friction, viscous friction in this case, and the control law are there. So you close the loop by replacing the expression of u in the second line into the first, on the right-hand side of the equation in the first line. We will use a Lyapunov candidate. The Lyapunov candidate is a variation of what we have seen so far. So it includes the control terms related to the proportional error. We have interpreted this as being a virtual spring that brings the error to 0 while moving in this case. The first term instead is a modification of the kinetic energy, because there is no Q dot as external vector, there's instead the velocity error E dot. Still, this function is positive definite and is 0 only when position error and velocity error are both 0, so when we are following the trajectory. So it's a good candidate. Its derivative is taken in a much similar way as we've seen before. So we have a term, we have two terms coming from the first addend. One is with the time derivative of the inertia matrix, and then the second is the contribution of two differentiation with the same scalar term, so the factor 2 vanishes, and we have E dot transpose M of Q times E double dot, so the second derivative of the error. And then the second component in the Lyapunov candidate produces in the differentiation E transpose Kp E dot, and we have seen this before. Now we will replace in this expression, so we have to evaluate this time derivative along the trajectory of the closed loop system. So we replace MQ E double dot, but we have to build first this expression. So if we look at the closed loop system, you can realize that there's an inertia matrix pre-multiplying Q double dot on one side and Q double dot desired on the other side. So if you bring those two terms on the same side, you build the acceleration error E double dot. And then you bring everything else on the other side, and you recognize that with a minus sign, there's the S matrix factorizing the Cauchy centrifugal term, multiplying Q dot desired minus Q dot, so E dot. And similarly for the viscous terms and for the derivative terms, and in fact they play a similar role as we have already discussed earlier. And finally, minus KPE. So we have this expression, and we can replace M of Q E double dot into the derivative of the Lyapunov function. By doing this and using the skew symmetry property M dot minus 2S in a quadratic form, which now externally has E dot transpose E dot, vanishes, and what remains, the other terms cancel the last term in the cross product of E transpose and E dot. So what remains is, as expected, I would say, the quadratic term with a minus sign and positive definite matrices KD and FV because of physical properties, KD because of our choice. So this is less or equal than 0. And is 0 only if and only if E dot is equal to 0. Now this looks like what we found, for instance, for the PD control law, but we cannot now directly apply LaSalle in order to make a conclusion about asymptotic stability. So far we have just shown stability of the error. Why is that? Because the system is time varying because of the presence of the trajectory error. Sorry, of the time varying trajectory. In fact, if you look carefully at, for instance, at the expression of the Lyapunov candidate, you find a dependence on E dot, and on Q. Now we know that the state vector for this system is a 2n dimensional vector, so E is n dimensional, E dot is n dimensional, and Q is n dimensional. But of course, one of these three quantities, in particular Q, I would say, must be written in terms of the other one. And if we replace in all the expression Q by Q desired of t minus the error, so by the definition, and similarly for the velocity in terms of Q dot desired of t minus the error, then we will rewrite everything as a function of the error state, E and E dot, and wherever you find Q desired of time, this will be an autonomous time varying quantities. So the Lyapunov candidate and the system in the closed loop is still is a time varying system. This is why we cannot directly, and in general, since the trajectory is not periodic, we cannot apply LaSalle theorem as such. So we have to go back to the previous block of slide, block number 8 and the slide 10, which I will do right now. And we have on this introductory part on stability of dynamical system, we have considered also this time-varying case, and in fact we are exactly in the application of trajectory tracking control for robots. Now in this case we had this Barbara lemma, which at that time when we talk about this, introduce quickly this aspect, was a kind of unidentified flying object, in a sense. Why do we care about this? But if we look carefully now, we have exactly this situation. If we have a generic function, function of the state and of time, like our candidate, which is lower bounded, and this is indeed true because our candidate is greater or equal than 0, so it's lower bounded from below from 0. And its time derivative is less or equal than 0, and this is what we have just shown. Then we can conclude that as time goes by, so for time going to infinity, there will exist a limit for the function v. However, we have no assurance so far that this implies also that the derivative will have a limit equal to 0. So if there's a limit for v, we may assume that this is a constant, in fact, but this does not imply in general that v dot will go to 0. Why? This is a strange mathematical phenomenon. You could have, let's say, fast oscillation, so the limit is still going to a constant, but the derivative is not going to 0. However, if in addition the second derivative of this function, in our case the Lyapunov candidate, is bounded, then this is sufficient to prove the thesis of this lemma, that there exists a limit also for the derivative of this function, and this is equal to 0. As a corollary, then, if we have a Lyapunov candidate, like in our case, that satisfy Barbara lemma, in fact, the first two assumptions, I and double I, are satisfied, we need to prove that the third one is also holding, then we can directly apply LaSalle theorem without caring about other further details. So, with this in mind, let's go back to our situation, and we have the Lyapunov candidate. We have seen that this is a time-varying function. The closed-loop system, in fact, it's a time-varying one. So let's check the assumption of Barbara lemma. So as we have said, the first two conditions are already satisfied. So the candidate, Lyapunov candidate, is lower bounded, and its time derivative is less or equal than 0. Then we have to check the boundedness of the second derivative. Now, if we go back to this situation, we have that v dot is minus e dot transpose kd plus fv e dot. So we have to take the one more derivative of this quantity in order to have v double dot. So v double dot is simply, since the matrix inside are constant, and again we have twice the derivation of the error terms out of e dot, so we have minus 2 e dot transpose kd plus fv e double dot. And our question now is to ask if this quantity is bounded. First of all, we should derive also the e double dot from the equation. Now, the first two assumptions that we are verified, and the fact that v is bounded, in fact, implies that since in the function v we have e and e dot, and everything is bounded, this means that also the error and its time derivative are bounded. Now, if we assume, like it is reasonable, that the desired trajectory has a bounded velocity, otherwise we would have a motion that goes to infinity, in a sense, then being e dot bounded and q dot's desired bounded, this implies also that the velocity itself of the robot will be bounded, so q dot is bounded. There are other two properties that we are using, namely intrinsic to the dynamic model terms of any robot. So from the positive definiteness of the inertia matrix, this implies also that its inverse is both lower bounded and upper bounded by some quantities. So m of minus 1 of q is a bounded quantity. Moreover, for any factorization of the coreous and centrifugal term, which are quadratic terms in the velocity, so if we factor out one velocity q dot, the remaining matrix S is linear in q dot, so it can be bounded because of the trigonometric dependence on q by some positive constant alpha times the norm of q dot, which is appearing linearly inside the matrix. So, with all this in mind, we look at the second derivative of E double dot. And from the previous expression of the previous slide, we have that E double dot, in fact, is minus m to the minus 1, and then the following terms in the square brackets. Now, the inverse of the inertia matrix is bounded in norm, so it's bounded itself. S times E dot is bounded because we can bound S by alpha norm of Q dot, but then Q dot is bounded itself, E dot is bounded as well as E, and so all these terms that are present in this right-hand side are bounded, and which implies that V double dot, which is a form which contains E dot and E double dot, all these quantities are bounded, so we are in the assumption of Barbara lemma. Which means that the time derivative of the Lyapunov candidate, as time goes to infinity, goes to 0. So we can speak about a set where V dot is equal to 0. So this is the whole story, which is the argument used in LaSalle. So now, just forget everything. We apply LaSalle as such. So we have seen that V dot is equal to 0 if and only if E dot is equal to 0. So the previous proof was meant to show that we can consider the set of state V dot equal to 0 as a converging set of states. Now, let's look what happens when V dot is equal to 0. So when E dot is equal to 0. So again, we look at the closed loop dynamics that we had in the previous slide. Let's go back now. Closed loop dynamic is expressed by the last equation. You can see that on the right-hand side there are E dots that now goes to 0. So what remains is just inertia matrix time E double dot equal minus Kp, the position error. So either the position error is 0, so the acceleration error will be 0, and we will remain in the set of states that 0, the derivative of the Lyapunov candidate. So this will be the invariant set of interest. Or the error is different from 0, and so the acceleration error will be different from 0, and we will leave this set, so this will not be an invariant set. So the conclusion follows from LaSalle. So the largest invariant set contained in the set of state at 0, the derivative of the Lyapunov candidate, is given exactly by the origin in the state space of errors. So E equals 0 and E dot equals 0. So global asymptotic tracking has been achieved. Global because we have not set any limitation to the initial error in our analysis. And this ends the proof. Now, we may consider some special case. So far we have considered that we have a trajectory, a time-varying trajectory. What happens if this trajectory vanishes into a constant or just stops at some times? Do we have any simplification in the control law that we have introduced so far, and we will make a comparison between these two control laws, namely feedback linearization, which is, as I said, in the assumption of having a good model of your system, the best performing controller, and this global asymptotic tracking controller that we have just talked about. Now, if you look at feedback linearization control, so the computed torque with the PD controller, in fact, if you set Q dot desired and Q double dot desired equal to 0, namely that you're considering the regulation task with QD constant, there are no special simplification. Why? Because you're cancelling stable dynamics no matter how, so you're cancelling the gravity term, the coresistance integral term, you're pre-multiplying the PD controller by the inertia matrix evaluated at the current configuration. Within the square bracket, the Q double dot desired term vanishes because the acceleration desired is 0. And also in the error of the velocity, you have a simplification. So you have, instead of KD times Q dot desired minus Q dot, you have only minus Q dot remaining. So there are no special simplification when you're using feedback linearization in the regulation case. However, this controller still fully linearizes the system and provides asymptotic stability of the error. So we have, in fact, exponential stability with decoupled transient using this feedback linearization control, but no simplification. Instead, when we are using the alternative global controller, we see that because of the presence of Q double dot desired and Q dot desired inside the expression, all this goes to 0, and what remains is only the PD term, which has the same form as in the feedback linearization 1, but no pre-multiplication by the inertia matrix, and the gravity term. So this, we recover what we have seen already, namely that PD plus gravity cancellation control is a global asymptotic stabilizer for the regulation task. So the trajectory tracking controller that we have seen so far naturally reduced to what we have seen before, while the feedback linearization controller remains the same even if we have regulation as a special case. In all these cases, however, we need information about the model. The complete model for trajectory tracking, at least the gravity term for regulation. We have seen that for regulation we can get rid of the information on the gravity by the iterative learning scheme or by using a PID controller with the integral term saturated, the argument of the integral term being saturated or being bounded in some way, but with additional condition on the gains. What if we don't know much about the full model and we still would like to have good tracking of a time-varying trajectory? This lends to the second part of this lecture, in fact the final part on trajectory tracking. So execution of a trajectory without having a model, or without having a good model to start with. So the question is, if we have reduced or really very poor information on the robot dynamic model, can we hope to accurately reproduce a sufficiently smooth joint space reference trajectory? This is our quest. And in fact, the answer, as you could imagine, is yes, but we require a special condition, operative condition. Namely, we require that the motion is repetitive. So it's a task, it's a trajectory task that has to be repeated over a finite interval of time, a certain number of times, actually a very large number. This is not a very unusual situation, for instance, in industrial application, because in fact, while we can reprogram for any new task the robot, but once an industrial robot has been programmed for a task, it repeats this task 10,000 times, I don't know, a huge number of times. So we may allow to do the task a few number of times before getting into operation until we achieve enough good performance in tracking the desired trajectory. So we may allow iterate or repetitive trials, not too many probably, and learn in a sense what we would like to, the command that allows us to do perfect tracking. So learning the inverse dynamics now in the general trajectory tracking case. So we have the following operative condition. We do a trial. We start from an initial condition. Of course, in this trial, we apply some controller, and as is stated in the third item here, this controller will have a non-model based part, so something that we can apply without knowing the dynamic model of the robot. And we have seen that the standard solution here is to use a PD control law, decentralized in the sense that we can use diagonal gains. And we will add to this a feed-forward, not a constant feed-forward, but a time-varying feed-forward. To start with, we will use typically zero feed-forward term, like we did in the iterative gravity compensation learning strategy. Now, we do once the trajectory. Typically, we have an error, so we record the error along the trajectory over a finite amount of time, between 0 and capital T, and we process this information offline in order to generate the new time-varying feed-forward for the next iteration, from the kth iteration to the k plus 1 iteration. There's a strong condition, however, that every iteration should start from the same initial position and typically with zero velocity. Okay, so under this condition, if we're able to prove that we converge to the right command, then we will have what is called iterative trajectory learning. So it's iterative in the sense that you repeat several times the same motion task until you converge to the desired high quality performance. So this approach has been pioneered by a Japanese researcher, Professor Arimoto. We've been doing some activity on this many years ago, and I would like to introduce, since the methodology is kind of sophisticated, like in most cases when you have a simple control method, it's very hard to prove its nice characteristics. Instead, if you have, like in the feedback minimization controller, a very complex control law, typically, as a rule of thumb, the analysis is simpler. So the analysis of this method of iterative trajectory learning is in general quite delicate. But this is why I will present this first on a simple system, on a single input, single output, linear system. So we will use Laplace methods in order to do the analysis. This is not just an academic example, because in fact this is a design method. So acquiring information on how to design the learning algorithm in this case is exactly preliminary to the application of this to the to a robot system. So here you see a standard linear control loop. You have a plant described by a transfer function. All signals are scalars. So you have an input u and an output ui. You do a unitary feedback loop. You compare the evolution of the control output with the reference trajectory y desired of t. You generate the error, and you apply a controller, which in the Laplace domain is represented by another transfer function xi of s, in order to generate the input command to the plant. Now, the input command, however, in this case, includes also a feed-forward term, which we call V, and in fact, VK will be the feed-forward at the kth iteration of the learning strategy. And for the same reason, we give a special name to the feedback part of the control U, which will be labeled with a prime. So U prime of T is the control produced by the feedback controller. So in general, it will be a U prime K if we are doing this at the kth iteration. Then we have a learning algorithm which uses the previous feed-forward term VK and the current control effort in the closed loop to generate the new offline, the new feed-forward term, VK plus 1, then you increment the index K, and you will apply this feed-forward during the trajectory execution at the next trial. So this is the whole strategy, and you have to initialize at the first trial the feed-forward, and typically you set V1 of T identically 0. And this is, in fact, this type of structure is very convenient because you can start with any controller that guarantees some stability to the closed loop system, but poor performance in terms of reproduction, the output Y to follow a desired trajectory Y desired. And then you can plug in this feed-forward and do some trial without touching the original controller. So this is a very convenient application. In fact, this strategy has been used in industrial processes for many other applications, wherever you have repeatability of tasks, so tasks that needs to be repeated over and over. There are a number of transfer functions that we need to use and of signal to be processed. So this is the closed loop transfer function without the learning part, so without the feed forward. It's just the product of the two transfer functions in the direct path, P and C, and then 1 plus PC. So this is the closed loop transfer function W of S, which relates the Laplace transform of the reference trajectory YD to the Laplace transform of the output Y. The control law at iteration K and the Laplace transform of these quantities will be labeled with a UK of S, which consists of the feedback part, UK prime of S, and the feed-forward part, VK of S. And of course, the feedback part will be processing by the controller, so the transfer function Chi of S multiplying the error at the iteration K in the Laplace domain. And similarly, the output in the presence of both the feedback and the feed-forward action at iteration K, so Yk of S in the Laplace domain, by the principle of superposition, you can apply a desired reference YD or a feed-forward VK. If you apply both, you have the superposition of the two transfer functions. So WS, which was the input-output transfer function, times YD of S, and the closed-loop transfer function from VK to Y, which is P of S, 1 plus PC. Now, in the next slide, which I use as a whiteboard, so I'll go step to step, I will prove this relationship, in particular the input-output transfer function and the feed-forward to output transfer function, and something more for those of you that have not taken a basic course in automatic control or do not remember well this concept. So first of all, remember that moving into the Laplace domain, so using this mathematical transformation, allows to deal with linear differential equation, solution of linear differential equation, by moving them into polynomial equation, so making algebraic transformation and manipulation which are much simpler, and we will see what this means. So we will use Laplace transform of all the signals involved. Indeed, we represent the plant and the controller with their transfer function, and we will use this notation with the complex variable s for all these listed variables. So, first of all, let's find out why the closed-loop transfer function of a unitary feedback loop, like the one that is shown in the diagram, takes the WS form that we have seen before. And you do computation really by product and sums and isolating terms, like when solving an algebraic system of equations. So y of s is the product of the transfer function of the plant times the input, u of s. The input is the sum of the feedback part of the control and of the feed-forward term. So apart from iteration, so the k is not here in this case, so we have v of s plus u prime of s. U prime itself is the output of the controller, so feedback controller, so chi of s times the error, and the error is the difference between the reference trajectory yd and the output trajectory y. Now at this stage you find that in this equation you have y of s on both sides of the equation, so you can isolate, bring the second y of s on the left hand side and obtain this expression. So you have 1 plus the product of p of s and chi of s times y of s equal whatever is left on the right hand side. And now you divide by the factor multiplying y of s, and you obtain, in fact, what we have seen before. So the in this feed forward plus feedback structure, where the feed forward later on will come from the learning algorithm over the iteration. So y of s is w of s, which has the form p times c over 1 plus pc, plus another transfer function, which is the one from the feed-forward input to the output, which is simply p over 1 plus pc. You see that all the, if you now rationalize this transfer function, because the numerator and the denominator are both rational functions, so they are ratio of polynomial expression, so you can rationalize all this transfer function, you will see that the denominator is always the same. So any closed-loop transfer function, no matter which input signal and output signal you're considering, have the same denominator, which is associated to the poles of the closed-loop system, and the poles are associated to the dynamics of the closed-loop behavior. Now, let's do two more computation, which will be useful later on, and consider the expression of the feedback controller at iteration k. So we have u prime k of s. This will be the output of the controller, so chi of s times yd of s minus yk of s should be in this case. So the first term remains the same. Yk of s is the result of the process of the plant processing the input, so we have to multiply by p, and then the input has the two contributions vk and uk prime. So again, you see that uk prime is at both sides of this identity, algebraic identity, so we can isolate uk prime on the left hand side. It will be 1 plus pc uk prime, and then all the rest remain on the other side. Then we divide by this factor like we did before, and we obtain again the uk prime as a contribution of two transfer functions, one from the desired input and one from the feed-forward term, and we will call the first transfer function W of C, because it relates the desired trajectory to the actual feedback command, while the other transfer function is just the opposite of the input-output transfer function that we have seen before. So this is not new, just a minus sign, because there's a minus in the loop, in fact, going from Vk to Uk prime. And finally, for the error at iteration k, we have a similar expression. So A of k of s is yd minus y of k. Again, there's a mistake here. Y of k is what we have just computed. In fact, it's w of s of y desired plus w of v, the transfer function above, times vk. And now we have a yd appearing in two terms, so it's 1 minus w of s will be the transfer function between the desired output trajectory and the error at iteration k. And in fact, if you look at the expression of w of s, which is pc over 1 plus pc, 1 minus w of s is another transfer function which is called the error transfer function in the elementary theory of feedback linear systems. So this full expression is y 1 over 1 plus pc. So we have all set, and I think that if you look again to this slide, even those that are not familiar with this concept will find things more clear. So let's go back to our learning update law. We have to define the way in which the feed-forward term is being changed from one iteration to the other. And the method that we proposed was combining through suitable filters, in the sense they are transfer function, the previous feed-forward term, Vk, plus the control effort that we had during the kth iteration. Remember that this operation is done offline, so we have stored the previous feed-forward over the whole trajectory between 0 and t. We have stored the control effort, the feedback control effort that we have applied during the previous iteration. Now these signals can be processed in the Laplace domain, and they can be filtered by suitable alpha of s and beta of s. And since we are doing this offline, and we have at the disposition all the sample over the whole trajectory duration 0 capital T, then a generic sample may use information that comes from samples that are before and after that instant, just because all the samples have been stored from the previous iteration. So this is the general format. Of course, alpha and beta are the design parameters in this update law, and they should satisfy some condition in order to guarantee that we will converge to some desired behavior. And in fact, we can write with some mathematics that we will detail in the next slide, the recursive expression of the feed-forward term. So Vk plus 1, you can see, takes the form written in the slide as a function of the desired trajectory, because it will depend on the desired trajectory, of course, and on the previous feed-forward term. And similarly, we have a recursive expression also for the error, because in fact we would like that the error converge to 0 or converge to some small values, if possible. And this is the expression that we will prove in the next slide. But you can see here that there are some similarities. In fact, in this recursive expression, when we are looking at the same variable, so at instant k and k plus 1, we see that there's a common factor, beta minus alpha of s, w of s, appearing. While the other terms depends only on the desired trajectory. And if the desired trajectory is repeated from trial to trial, so it's always the same, when we look at the variation, this term will vanish. Again, we will see this in the next slide in more detail. So now, looking at this expression, we can say that if the module of this complex number beta of s minus alpha of s w of s is less than 1, and this could be for any value of s, and in particular if you substitute to s j omega, so you look at the frequency analysis, if this is true for all frequencies, or at least if it's true for a certain interval of frequency, then you will have convergence in that domain of frequency, or for all frequency, as k goes to infinity. Convergence means that vk plus 1 in the Laplace domain, but also, of course, in the time domain, will converge to a specific profile, as well as the error will converge to a specific profile, hopefully identically to 0. And in fact, the Laplace transform of the limit value for these two scalar signals is given by these two expressions. Please note that, for instance, in the second one, if beta equal 1 can be chosen, so that we guarantee that the contraction condition is satisfied by some choice of alpha and by beta equal 1, then since 1 minus beta is at the numerator, this term will vanish, and the error at steady state of this iterative learning strategy will be 0. So we will have perfect tracking. Indeed, if we choose beta different from 1, then we will have some error which changes expression depending on the frequency of interest. So, before making these conclusions, let's look at how we find the recursive expression for the feed-forward term vk and for the error pk, so the formula that I written directly in the previous slide. So again, we're using the whiteboard, so we'll do the individual step in this derivation. So, first of all, the update law is vk plus 1 equal alpha uk prime. Remember, the uk prime is the feedback control effort at iteration k plus beta of s vk. Indeed, uk prime is nothing else than c times the error at iteration k, and the error at iteration k, we have written its expression in terms of transfer function, is the error transfer function, so it's 1 over 1 pc, 1 plus pc, yd minus the transfer function from the feed-forward to the error times vk. And now you see that we have vk in two parts, and we substitute the expression for the transfer function that we found before, and we have exactly this recursive expression where ac over 1 plus pc multiplies the desired trajectory in the Laplace domain, and the factor beta minus alpha times w of s appears in front of the previous feed-forward term. And on these quantities, in fact, we do contraction. While a bit more involved is finding the recursive expression for the error ak, so ak plus 1 as a function of yd and ek. So first of all, the definition of the error at the iteration k is yd minus yk. Yk, so the output of the system during that iteration, is the output of the plant, P of S, multiplied by the input, which is the sum of the feed-forward and the feedback terms. Now, from this equation, we can isolate Vk. So we bring Yd to the other side, we change sign, we divide by P, and then we subtract Uk prime. And so we have that this equivalent expression that we will use in the following, Vk is given by this expression in terms of the error and of the desired trajectory output, and also of the case feedback control action. Now, if we look at the output at the next iteration, so k plus 1, this will be given by the output of the plant times the output at that iteration, which is the sum, the input at that iteration, which is the sum of the feed-forward Vk plus 1 and the feedback action U prime k plus 1. And Vk plus 1 has the update law, so we replace this with A times U prime k plus beta alpha times UK prime plus beta Vk. And now in Vk we substitute the previous expression. Why are we doing this? Because by doing so we will end up with an expression that will be used for finding the recursion for the error. So we do this substitution. There's still a bit of simplification to do. So we have the first term is P is in front of everything. Then alpha times UK prime. UK prime, of course, is the controller times the error AK. Then we have beta times Vk, and we replace now the expression of Vk of the previous identity, so 1 over P times Yd minus Ek, and then again minus beta times the UK prime, which is C times Ek, and finally plus UK prime, which is written as C times Ek plus 1. I think everything is there. Also the parentheses are set in the right way. Now you can see, for instance, that the terms Yd, which appears in one of the elements, is pre-multiplied by the plant process, the plant transfer function, so P of S times beta times 1 over P. So it's only multiplied by beta. So this observation is useful because when we are finally writing the error at iteration k plus 1, which is Yd minus Yk plus 1, and we use the Yk plus 1 before, so we have Yd minus wherever we find Yd, which was just beta times Yd of S, and then you substitute all the rest of the expression with a minus sign, grouping what depends on AK and what depends on AK plus 1. And finally, in blue, I highlighted where AK plus 1 is found on both sides of this identity. So you bring the second term to the left-hand side. So you have a 1 plus PC times AK plus 1. And then you divide by this, and you obtain the final formula. So this was a bit more complex, as you can see, as before, and the final formula has one term which depends only on Yd, and the second term, which is an elaboration of the previous error at iteration k by the same filtering action beta minus alpha W of S. So now we have given the recursive expression of the feed forward and of the error, and we have said that under the contraction condition we have some limit values for these signals. So let's prove that this is true. So we have the recursive expression written again in this slide, and now we make a difference between these values and the values that they had at the previous iteration. When we make the difference between this, of course, what is repetitive in the expression just vanishes. So we compute the variation from k to k plus 1. For the feed-forward term, we have delta Vk plus 1, which is defined by Vk plus 1 minus Vk, and Vk has the similar expression in terms of Vk minus 1. So the terms depending on Yd is the same, and in the subtraction is being eliminated. So what remains is beta minus alpha w of s times the variation at iteration k, which is vk minus 1. And the same story happens for the error. I don't have to comment it again. And now you see that it's the variation that contracts. So if the assumption holds, so that the absolute, the modulus of this complex factor is strictly less than 1, then the sequence of vk and the sequence of ek converge to some limit values. How do we compute these values? We just take the first two relation in this slide and set vk equal vk plus 1 equal v infinity and ek equal ek plus 1 equal e infinity. So you write the following one, and now you again isolate v infinity and e infinity, so doing again algebraic manipulation, and you find the two expressions that I gave 2 slides ago. Now, we make the same consideration that we've done before. So now look what happens if we are highlighting some of this expression. So first of all, if beta is equal to 1, then the limit error will go to 0. So we will do perfect tracking. And in the same way, when beta is equal to 1 in the first expression, you will see that the numerator and the denominator of the second factor becomes the same, so they can be eliminated, and what remains is just yd over p, which is nothing else than the inverse dynamics of our plant. In fact, at steady state, the feed forward is exactly the desired trajectory divided by the process. And if we put this as input to the process, there will be a cancellation between the PS at the numerator and the denominator, and the output will be exactly the desired one. So we find very nice that under these conditions, the error will go to 0 and the input will be the inverse dynamics input. Of course, this is a simple input single output case, but the same type of behavior with some difficulty related to the fact that we have nonlinear dynamics and multi-input, multi-output system will be found on the robot application. So let's summarize our analysis. So if the choice beta equal 1 is admissible, so it guarantees together with alpha that the contraction condition is satisfied, then there will be 0 tracking error when the scheme converge. And the inverse command, the feed-forward command will be the inverse dynamics command that we have learned over the iteration. As you can see, like in real life, doing errors is more helpful in order to learn better than doing things right from in the first place. So this, let's say, philosophical consideration can be applied also to this type of control laws. Now, what about alpha? Indeed, if you can set alpha equal 1 over w of s in these formulas, under the assumption that beta is equal to 1, then you would do one time under some stabilizing controller the execution of the trajectory, you record the error, and then in the next iteration you will converge to 0 error. Of course, this assumption implies that you know perfectly the plant. But in fact, what you need to know is not the open loop plant, but the closed loop transfer function. So the closed loop plant under the action of your controller. And this makes a huge difference, because while it is true that perfect knowledge of W is there only if you have perfect knowledge of P and of course of C, but this is trivial because the C is your controller, so it's what you have designed, so you know very well what is the structure of C. So, as I was saying, while this is true, however, the closed loop system is much more, let's say, has a behavior that you can expect much better than the original plan. This is the whole benefit of using feedback in order to control the system. All the system tend to behave like you expect. So what I'm saying is that you don't need an accurate knowledge of P in order to make a choice of alpha which is similar to 1 over WS, so it's not exactly that, and you don't need much information about the original plant at this point, so you don't converge in one iteration, but the number of iterations will be a finite one, and the performance will improve over and over. So all this, of course, is true if you're allowed to use beta equal 1. If instead you are not able to converge when you're using beta equal 1, this approach allows you to get convergence, although you tolerate some error. And typically this happens when you have high frequency dynamics that you neglect in your modeling. Beta of S is there in order to cancel out or filter out, better said, this high frequency dynamics, which would bar the possibility of convergence. So you get convergence, the price you pay for getting convergence is that you don't reproduce exactly high frequency dynamics of your trajectory. Okay? So, final consideration, as you can see, I've been talking about linear concepts so far, even for one input, one output only. But in the synthesis of each pair of filter, alpha and beta, for each joint of a robot, still this classic tool from a linear system can be used. For instance, you can use Nyquist plot to show the behavior or the approximate behavior of the term beta minus alpha of W of S, and if the Nyquist plot, like in one of the two graphs in the picture, is all internal to the unit circle, then you will have the contraction and the scheme, the iterative scheme will converge. If not, you may have convergence only for a certain number of frequency up to an upper bound, let's say omega 0. Okay, so to conclude, let's see how this method is being used for designing an iterative learning controller for an n-dimensional nonlinear robot. So suppose that we model the robot as the first equation, which is including the inertia of the motor, so we are assuming that there is no elasticity of the joint, so we know that adding the inertia is like adding a diagonal term, a constant diagonal term to the link inertia matrix M of Q, and suppose there is some viscous friction present, and that this part is reasonably known, and then the other terms are the one that we've seen before. And suppose that the first feedback controller, or the feedback control law that you're using, is a PD control with partial cancellation of gravity. So we are using, of course, G hat, because we don't know exactly the expression of G. And similarly, we don't know exactly the expression of the constant term in the other part of the model, namely of Bm and Fv. But if we approximate the system around the given trajectory, we end up for each joint having a transfer function of this form. So this will be the W of I of S, and you can see that the numerator is given by the PD gains that have been chosen by us. The denominator is a second-order system with an uncertain inertia of the motor, B hat, an uncertain first-order term, which is, however, can be dominated by KDI, and a known term at the degree 0. So you can see that this transfer function contains only little information of the original system, but maybe enough to design the learning filters joint by joint, and then through iteration to have a convergence to a reasonably good execution of the original trajectory. What is missing is the initialization. As we said, in the worst case, you just set V1 to 0 for the feed forward. But in fact, if you have any information about the dynamics of your robot, then you will use this in an inverse dynamic fashion. Of course, all hats may represent estimated value, whatever best estimate value you have. If you don't have any estimated value at all, you just simply set V1 equals 0, and you will have, probably, you will need more trials to converge. Now, I'm presenting some experimental results that we obtained many years ago on a prototype that was given to our department, which at the time was named DIS, or Dipartimento di Informatica Sistemistica, not DIAC like now. So this robot was a 6-level joint robot, and we perform experiment with joint 2 and 3, so in a planar vertical plane. Another feature of this robot, this prototype, was that there were springs mounted in the structure balancing most of the gravity, so about 90% of the gravity. It uses harmonic drive, so there are also effects in the high frequency domain that were neglected, and this is another reason why the beta function filter is needed. And the most striking point is that this system had a high level of dry friction, so friction not modeled by viscous one, and very time varying over iteration. So this was using it, if I remember well, at that time, almost 50% of the total torque was needed to overcome this type of friction, or kind of a non-efficient situation. So this system lends itself to a very nice application of learning control, because the model that you may derive following the Euler-Lagrange equation or methodology, it's not really capturing this essential part of dry friction of your dynamics. And identifying this part is also quite difficult. So we moved both joints with the following velocity and position profile, and you can see that the velocity reaches a top value of 50 degrees per second, and then reverse, it's a trapezoidal profile, and the position moves from the initial configuration to 160 degrees and then comes back. So this is a periodic trajectory. So from one execution to the other, we start from the same zero velocity and same configuration, and we end at the end of the 9 seconds or so of trajectory in the same configuration, at least ideally. Okay, so the fact that we are reinitializing the system is obtained by choosing a periodic trajectory. The reinitialization will not be exact, so there should be some perturbation to the scheme, but the scheme is robust enough to guarantee convergence anyway. So the control architecture was very outdated, I would say. We were using the DSP, we were using an IBM PC XT286. You may have never heard about this. The robot itself had DC motors with current amplifiers, so we were commanding current in place of torques. and it used resolvers and tachometers. So has no, at that time they had no digital encoders, and they have already still mounted tachometers. But this, as I said, were presenting some noise effect. So you see the full organization. So on the PC we did supervision and learning. So offline we were processing the data that were acquired from the experiment through our sensor and through the motor commands. The control in real time was handled by the DSP device, and everything worked at the frequency rate for the DSP of 400 microseconds, and you can see also other conversion rate between analog and digital results. For instance, R2D is the resolution of the resolver to digital, 16-bit used for the 360 degrees. So the results looks like this. So these are joint 2 on the left and joint 3 on the right, and these are the error profile that we obtain at the iteration 1, at the iteration 3, 6, and 12. And you can probably recognize that the initial error was not so large, so we have a peak of about 1 degree, but this value is being reduced over the iteration to about 0.2 degrees, so a factor of 5 with 12 iterations. So the error is going to be reduced. There is some residual error left because we have used here a beta different from 1, because otherwise the system did not converge because of the presence of high frequency dynamics in the elasticity of the joints and other effects that were not considered. But still we get some convergence. And similarly, in this other pairs of plots, again on the left for joint 2, on the right for joint 3, on top the feed forward over the iteration, and below the feedback action over the iteration. And indeed the feed forward at iteration 1 is 0, so you see no plots, but while moving from iteration 3 to 6 to 12, you see that there is increase of the feed forward. The scale is in ampere because these are currents, so we get from 0 ampere to about 5 at iteration 3, and then 10, and then over 10 at iteration 12. Both, at least for joint 1 and for joint 2, sorry, and for joint 3, the value of ampere are a little bit less, so but at the 12th iteration we are around a peak of 5-6 ampere. So the feed forward is acquiring the inverse dynamics of the plant needed to reproduce with a reduced error the desired trajectory. At the same time, and this is also interesting, the control effort of the feedback term is being reduced, because the feedback term is there because there's an error in executing the trajectory. If this error is going to 0, of course, the feedback effort is going to 0 as well. And in fact, complementary to what you have seen on the feed-forward plots, the feedback plots shows a decrease from iteration 1 to 3 to 6 to 12 of the control effort due to feedback on joint 2 and on joint 3. And this concludes this part of the course. Thank you for listening.